use and apply algebra. We're going to use algebra to show that statements 3 and 4 are equivalent. We're going to use good old algebra, ladies and gentlemen. Okay, Frank, any questions? Okay, class, please copy this. My student, please copy this, and then we're going to move on. Okay? So I'm going to pause the video, give you an opportunity to copy this as the rest of the class is copying this. Then we're going to move on, because I'm going to need to erase this. But this is how you should be presenting your work. You should make clear statements as to what your goals and your objective is in accomplishing something, improving something. Because this is just beyond the math. In life, when you have goals and objectives, you need to write down how are you going to get there. What do you plan to do to get there? What is it you're trying to show? So this is part of the thinking process, the critical thinking process of how we're going to do that. So you and the rest of the class, please copy this, and I shall return. I'll give you about a minute, and I'll pause the video to give you an opportunity to finish copying this. Harry, Sue, Victoria, Juan, Carlito, please. Thank you. Okay, at this time, if you have not copied the information, please pause the video and do so. Please do so. And I will be right back to begin showing how to use the algebra to show that statements 3 and 4 are equal to each other. Matter of fact, I'd like for you to think it over first and think about how would you use the algebra to show that statement 3 is the equivalent of statement 4. So I'll give you that time as well. And the rest of the class, I want you to think that over as well while you're copying this, and I'll be right back. Okay, ladies and gentlemen, at this time you should have had enough time to copy the information from the board. Now, we're going to move forward, and we're going to show how to use algebra. First, I want to ask a question. Veronica, Juan, between the two of you, did you come up with an idea of how am I going to use algebra to show that 3 is equal to 4? What concept would I use here to do that? What concept do I use on 3 to make the transition from 3 to 4 to show that 3 and 4 are indeed equal to each other? What concept would I apply here? Okay, Veronica, let me hear from you. Very good. Excellent. Yes, I totally agree. Very good observation. The rest of the class agree? Very good observation, Veronica. Very good. Do you see what Veronica saw? And do you see the concept? I believe deeply in the use of concepts. We have to know the concept, not just this is what you do. Because if you don't know what you're using, then it's useless. You have to know your tools. You have to know what it does and how to use it. Very good, Veronica. Excellent. All right, so do you have an idea of what concept can I use on this to transition this to statement 4? Please tell me. Okay, are you sure? I believe that you are in agreement with Veronica and the rest of the class. Yes, Juan? So let's see if your conjecture is correct. So, what we're going to do, we're going to take this equation. We have the limit of f of a plus delta x as delta x approaches 0. That's equal to f of a. So now to solve that equation, to transition that from this form to this form, what are you going to do? Peter? Yes, exactly what Veronica said. Very good. Good, you guys were paying attention, you saw what she said, and all of you came to an agreement. Do you see it? What do you think I'm going to do now? I'm waiting. What was that? Very good, yes. What I'm going to do, I'm going to need to get rid of the f of a. So in this case, I'm going to need to use the additive inverse and then the additive property of equality. Whatever I add to one side, I must add to the other. So no matter where you go in higher mathematics, all those concepts are continuously used. You must remember those concepts. Not just this is what you do, but what is the concept that you're using? That is very important as part of your critical thinking analysis. What is it that I'm using? What is it called? So, the additive inverse of f of a is minus f of a. When two additive inverses add or combine, they add up to 0. Now I added f of a to this side because this is just like a scale where they must remain in balance. Whatever I do to one side of the scale, I must do the same exact thing to the other to make sure that the scale remains in balance. So, in this case, if I add negative f of a to the right, I must add negative f of a to the left. Additive property of equality. Whatever I do to one side, I must do the same thing to the other. And please realize that f of a is a constant. It's a constant value. It's not going to change. It doesn't represent a variable. A represents some number. What number? We don't know, but it's a constant. So now, we draw a line, just like solving any other equation. Now we bring everything down. So now we end up with the limit of f of a plus delta x minus f of a as delta x approaches 0. That's equal to 0. So now, we have just shown that statement 3 is the same thing as statement 4. But you say, how is that? Well, what is this equal to? What is this equal to? So we can complete that. Yes. Harry? Aha, very good. And Juanita, you saw the same thing, didn't you? Very good. I'm proud of you guys. Give yourself a hand. Excellent. Very good. Let's show the student. Do you know what this is equal to? What? Very good. Yes. Right from here. We have it. We know that in this case, delta F is equal to F of A plus delta X minus F of A. See, you got me so excited about teaching you. You got me on my knees just teaching for you. See, I'm on my knees teaching. I'm so excited to be here and be working with all of you. There it is. That is why. So now we have just shown, and let me write that down. We have just shown that statements 3 and 4 are equivalent. So you've just shown that by use of algebra. Class, are there any other questions? Please look this over. I will take questions at this time. Carlito. Okay, so that's clear to you now. You see that, and also just from the basic line segment, the geometry that we applied. See how powerful those small things are. They seem small, but they're powerful because these are used in even the higher level in advanced calculus as well. We cannot forget these foundations. This is the foundations of going on and looking at metric spaces. Uniform continuity, which we'll be getting to. So, are there any other questions? Let's see. George? So you have a better understanding of that now. What about you? Is this clearer to you now? Very good. So what I'm going to ask all of you to do, I'm going to step back again. I'm going to give you an opportunity. I'm going to ask you to copy this. I'm going to wait about a minute. Then I'll pause the video for you so that way you can copy that down, and then I'll come back and close out. Is that all right? Very good. Okay. Okay, ladies and gentlemen, at this time I'm going to pause the video. Okay, ladies and gentlemen, so let me summarize what we have just done. Through our work, we have just shown that all these statements are all equivalent to each other. We showed that statements 1 and 2 are equivalent because they are simply the definition of continuity. And then for statements 2 and 3, by using the line segment, the algebra, and substitution, we showed that by substitution and that changing the form of this, that statement 2 is indeed statement 3. They are one and the same, just different forms. Then we went on to show by use of algebra that statements 3 and 4 are also indeed the same thing, that is written in a different form. So ladies and gentlemen, the vital thing to get out of this, you need to commit this to memory because this is going to be very important as we begin to look at and prove the theorem that says that if a function is differentiable at A, it is continuous at A. That these 4 statements are all the same ways, different ways of stating continuity, that a function is continuous at a point. So these are 4 different ways of saying the same thing. So these 4 statements are all equivalent to one another. That is very important. And I really wanted to make sure that I took my time, took questions, gave you time to think it through. Because this is going to be vital to your further study in calculus. So I implore you, if you need to, please rewind this video, go through it step by step, dismantle it, look at it, think about it. As one of my professors from Rutgers University, Professor Keyes, who I have a great gratitude and appreciation for, as he told me that I needed to step back, take a cup of cocoa, relax, and just enjoy the moment. And that when I did that, things would start to come to me. And he was absolutely correct. So I want you to enjoy the cocoa. Step back and enjoy it. Think it over. Let it come through. Remove any obstacles or stress and just focus on this. Get your favorite cup of cocoa or juice and sit back, lock yourself in a room, lean back and just look at this and think it over. So, thank you for joining me, the class, you. And next, we're going to look at showing and proving that if a function is indeed differentiable at a point x equals a, then it is continuous at that point. And we're going to be utilizing these statements, particularly this one. It's going to be essential. And we're going to show that. And also there's a wording there that we must pay close attention to. And that word is exists. So, until next time, thank you for joining me, and I'll